Sorry for that. The I knocked the camera out of the little stand I have it in, so I cut the ending of that video. Maybe I'll make a blooper reel for you guys eventually. But this is now part 2. So we left off on this problem, and I said you could go ahead and solve this on your own. But if you do solve it on your own and want to check your answer, the answer is x is approximately 0.73. All right, so if we want to now look at this new example called the equal logarithm property. So here's a couple of blanks I filled into the notes already. It's for any positive numbers b, x, and y. So in all the examples, b, x, and y are positive, and b is not equal to 1. Log base b of x equals log base b of y if and only if x equals y. So again, let's translate this into normal language. What we're basically trying to say is if I'm taking the log of something and I'm taking the log of something else, I'm using the same log base b, log base b. If I'm doing the same thing on each side, then these two numbers are equal to one another, x and y. Those numbers are equal to one another. So look at this example we have over here. Log base 4, 6x minus 16 equals log base 4, x minus 1. Well, we're taking the same log on each side. So essentially, they just cancel each other out. Now again, that's not proper math vocabulary. They don't actually cancel, air quote, each other out. Really, we just are rewriting an equation by equating these two values to each other. However, again, in our class, let's just say as, hey, if there's the same logarithm each side, they cancel each other out. So, continuing. Now we have an equation where we just solved using our Algebra 1 techniques again. Get our variables on one side and our whole numbers on the other side. All right? I'll leave the solving to you, but we'll put a ... for to be continued. You can do the math. Pause it right now if you want. And when you repause it, you'll see the answer. X does come out to be equal to 3 in this example. Again, get your variables to one side and your whole numbers to the other side. Solve for x. We have a similar example over here. I have the same logarithm on each side. That only happens, by the way, this little shortcut only happens if it's the same exact logarithm. Log base 6, log base 6. Because they're the same, then we can do this kind of canceling out shortcut. So we get to rewrite our equation. 7x minus 13 equals 2x plus 17. Solving, we can add 13 to each side. And we can also minus 2x from each side. We get 5x equals 30. If 5x equals 30, divide everything by 5, and x equals 6. That's the equal logarithm property. Now, that's a great technique if we have the same logarithm on each side. Well, as you guys know, that's not always going to happen. Sometimes we're going to have different logarithms on each side, like example 6. Before I get to example 6, make sure you reread what's up top here. It says when only one side of an equation is a logarithmic expression, you can exponentiate each side of the equation. That is, use each side of the equation as an exponent in an expression with the same base. So, for b is greater than 0 and b is not equal to 1, if x equals y, then b to the x equals b to the y. Again, let's translate that into a real example here. Basically what we're saying is, if I have an equation like so, I can rewrite this by making each part of the equation the exponent in a new equation. So watch how I would do this. And there is a reason why I'm choosing 5, which we'll review momentarily. I rewrote this equation. Notice how the original equation is now the exponents of this new equation. Each side has a base of 5. Now you have to have the same base. Like see up here, they did b and b in the example. Notice it's the same letter. We're doing the same number. Now there's a reason why I would do this. The reason why we would do this is exponents and logarithms are inverses of one another. Just like adding and subtraction are inverses. You see how exponents and logs tend to cancel each other out a lot of times. Well, that's the case right here. 5 and log base 5 cancel out. 5 to the second is 25. I would therefore be able to get this equation. And then I can solve this equation. Plus 8, 3x equals 33. Therefore, x equals 11. Now, another way of visualizing what I just did in that problem is to think about how you did the rewriting logarithms in our earlier section. We used to do 5 to the second power equals 3x minus 8, or 5 to the second power equals 3x minus 8. Well, that's eventually what I got in this equation, right? That's what I got on this line right here. I just did the 5 squared and I changed it into a 25. Using the exponentiating property or rewriting your logarithms into exponential form is really the same thing. It's just a different way of expressing that idea. Our last example of the day is this problem where we're going to have our check for extraneous solutions. I'll show you why. First thing we have to do is put this together. We're going to condense our logarithm. We can condense our logarithm, recall, plus, we're really going to translate that to multiplication. So we're going to translate as 5x times x minus 1 equals 2. So we condense the left-hand side into a singular logarithm. Well, rewriting this, I'm going to write this as log 5x squared minus 5x. We would get that by distributing 5x times x minus 1. Now we can exponentiate the equation. The exponentiate, or why we're exponentiating, is I want to get rid of this logarithm. I don't want that word log there anymore. If I put each side raised, or rather each side has a base of 10, right? Now these are both in the exponent. Log 5x squared minus 5x equals 10 squared. 10 is my base. These are the exponents. Log, if there's no base, has a base of 10. Therefore, log base 10 and 10 cancel each other out. 5x squared minus 5x equals 100. 100 is simply 10 squared simplified. All right, now everyone's favorite. We're going to be solving this equation through, drumroll, factoring. So let's get everything to one side of the equation and solve via factoring. Now when we solve via factoring, first thing you might notice is there's a GCF. We can factor out that GCF. Now we need to figure out how to factor this minus 20 that also adds up to negative 1. So factors of negative 20 that add to negative 1. Think about what those factors may be. If you came up with minus 5 and plus 4, then you're right. That would be the factoring. Remember, whenever, it's one of the biggest takeaways you can have from Algebra 2, is whenever you get a quadratic equation, like in this line, you have to solve by factoring, completing the square, graphing, or where I leave off, factoring, completing the square, graphing, or the quadratic formula. You cannot try to do the square root just because there's a square there, right? That only happens if we only have an x squared. We have this quadratic format. We need to use factoring or quadratic formula preferably. Now, once we're done factoring, we can see that x equals 5 and x equals negative 4 by using our zero product property. This is where we want to check for extraneous solutions. If I go back to the original problem, if I try to plug in x equals negative 4 back into the original, I would have log of 5 times negative 4 for that first part, or log of negative 20. You cannot take a log of a negative number. In fact, go ahead and try to type that into your calculator. You'll get an error message coming up. If your solution forces you to take the log of a negative number, then that solution is extraneous. Remember that definition of extraneous? It's just like an extra answer that we are not going to use. So even though I got two solutions, x equals -4, we would consider as an extraneous solution. All right? We'll see you guys. Good luck on the practice. Email me, message me, whether through Google Classroom, through our regular email. Let me know. Good luck. Have a great day, guys.